In this section, we're still working with derivatives, but we're starting to work with derivatives of another set of functions that heretofore I was not able to work with. So we're working with derivatives of trig functions. A couple of quick notes: when we're working with derivatives of trig functions, all the formulas that I'm working with here are in radians. So we are working in radians. If you want to talk about derivatives of trig functions in degrees, we have to convert our radians to degrees and work from there. So we're working in radians here is the assumption. Another thing that I'm a real stickler about and I'm going to be looking for all the time is that you should always put parentheses around the arguments of your trig function. So you should always put parentheses. You should always spell parentheses correctly. Okay, so you should always put parentheses around the arguments of your trig functions. Now, in this particular section, it's not going to matter a whole heck of a lot because our arguments are just x, but it will matter a lot once we learn the chain rule and we apply it to trigonometric functions. So for instance, if you have a function y equals sine of x, I don't want to see it written like this. I want to see it written as y equals sine of x. And this is my preference because pretty soon this argument is not going to just be x. It might be something like the sine of x plus 1, and then you might see it written like this, and then it's ambiguous. Is the argument x or is it x plus 1? So I insist that you always put parentheses around the arguments of your trig functions. I do not want to see them written without that parenthesis. So as we get started, there's some memorization that's going to have to occur here. You will need to memorize these 6 basic trig derivatives. And there's no two ways about it. They just need to be memorized. So the first one is the derivative with respect to x of the sine of x. Now I want you to recall that all of our derivatives here are with respect to x because our arguments are. I could say d theta of the sine of theta and it wouldn't matter as long as the variables match. If I had d theta of the sine of x, what that would mean if sine of x is just a constant, and my derivative with respect to theta then would be 0 because the derivative of any constant is 0. So I'm going to look at the derivative of sine, of tangent, and secant to get started. Okay, the derivative of sine is cosine of x. The derivative of tangent of x is secant squared of x. Notice the arguments don't change. The derivative of secant x is secant of x times tangent of x. Important thing to remember here is you need the argument after each of the trig functions. Now another quick thing I would like you to note is when we're working with these derivatives, I can prove that this is the derivative if you go through and apply some, again, the limit definition of the derivative, and then also if you go through and apply some rewrites using some trigonometric identities. Those are in the textbook. Look through them if you want to prove them. I'd be happy to sit down and prove them with you in my office as well. But for time's sake here, we are going to go through and work with these established derivatives. Now I'm putting cosine, cotangent, and cosecant over here for a reason. Now remember, our arguments are all x's here. In other sections, the arguments will become more complicated. So the derivatives of any of our tangent functions that start with a c, like cosine, cotangent, cosecant, are negative. So that's why I put them all together here on the right hand side, because they're all negative. Over here on the left hand side, they're all positive. So the derivative of any trig function that starts with the c will have a negative result. So the derivative of cosine is negative sine of x. The derivative of cotangent of x is negative cosecant squared of x. The derivative of cosecant of x is negative cosecant x cotangent x. Now if you remember your Pythagorean identities from trigonometry, the first one, which I'm sure you'll remember, is sine squared plus cosine squared is 1. So the way I remember my trig derivatives is I remember, okay, sine squared plus cosine squared is 1. Sines and cosines go together. Now, tangents and secants, if you remember from your trigonometric identities with the Pythagorean identity, 1 plus tangent squared is secant squared. Tangents and secants go together. And conversely, secants go with tangents, cosecants go with cotangents. So these simply just need to be memorized. Now when we start taking derivatives, let's start with some basics and kind of work up to some more complicated expressions. I could talk about the derivative with respect to x of, let's say, 3 square roots of x plus sine of x. Okay, well the first thing that we would typically want to do is rewrite this from from radical form to exponential form. So this would be 3x to the 1/2 plus sine of x. One thing that I'd like you to remember here, the 3 is not raised to the 1/2, just the x is. So when I take this derivative, I bring the 1/2 down, so I get 3/2 x to the negative 1/2. The derivative of sine of x is cosine of x. And always put parentheses around the arguments of your trig functions. So this implies that f prime of x, or y prime, is equal to 3 over 2 roots x plus cosine of x. Now this is the slope of the tangent line at any point along the graph. This is the slope of the curve at any point. So if I wanted to find the slope at a particular point, I would just choose a value of x. It has to be in radians, and I could find the slope and of course write the equation of a tangent line. Let's go ahead and look at another one where I have to apply the product rule. Let's look at x squared cosine of x. So the product rule says to take the first function times the derivative of the second function plus the second function times the derivative of the first function. Okay, so there's my setup. Now let's go ahead and run through and actually calculate this derivative. The derivative of the cosine of x is negative sine of x. The derivative of x squared is 2x. Now we have to be really careful here because the temptation might be to say, oh, I have two things in parentheses. When they're right next to each other I should multiply, but that's not the case here. You can't mess with the argument of a trig function unless you apply some double angle or half angle identities. So the x stays the same and this 2x is actually going to be pulled out front. And so when you rewrite these, always rewrite them with any negatives, any constants pulled out front. So this is going to look like negative x squared sine of x plus 2x cosine of x. Now if we wanted to simplify completely here, we could factor out an x, but I think this looks good. So let's go ahead and finish and make sure we write down that this is our f prime of x, and there's our solution. And up here we had our f prime of x as well. We always need to make sure we know what our function is and what the derivatives are. Okay, so that one was using the product rule. Let's go ahead and look at another one where we're taking the derivative with respect to x and we're using the quotient rule. That would be the tangent of x over x. Now, please never be tempted to cancel these x's. This x is in the argument of a trig function. It's not a factor, so I cannot cancel it. So I'm going to have to use the quotient rule here. So I'm going to start with the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Now this is just my strategy. This is not my derivative. So my derivative would be y prime or f prime of x, however you want to call it, or d dx. And I would take the derivative of tangent, which is secant squared of x. Now here, the derivative of x is an implied 1. I don't need to write it here, but I'm going to just fill it in so you can see that we actually did take that derivative. And this is all over x squared. So y prime is equal to x secant squared of x minus tangent of x all over x squared. Whoops, forgot to close that parenthesis. Okay, so there's our derivative. Now when we're working with derivatives, we can always check your answers. And if you're going to take multiple derivatives like second and third derivatives, I always recommend that after your first derivative, you simplify it and you check it in Maple or Wolfram or with your calculator to make sure you're in the right track before you spend too much time finding multiple derivatives. So let's go ahead and take a second to open up Maple and see if this matches. Okay, so here we are in Maple. Let's go ahead and input our function first just to make sure it's what we think it is. I can type in tangent of x, or if you see over here on the left hand side, I have these shortcuts that tell me what my trig functions are. So I'm going to have tangent of x divided by x. And let's see if that's what we think it is. Yep. Now if I don't put parentheses around the argument of my trig function, let's see what happens. It's just reading this as 4 letters, TANX. It has no reference whatsoever to the tangent function. So you have to put parentheses around those arguments. Now because it recognizes this as a complete function, I do not need to put parentheses around the entire function. It's not going to take that x divided by x. Okay. Now I want to find the derivative of this, so I'm going to right click and choose differentiate with respect to x, and there's my derivative. Now this does not look all that familiar. If you recall, we had secants involved in our solution, and we also had x squareds, and here I have x and x squareds and no secants. So we have to try and figure out what's going on here. Well, I could simplify this, so we could right click and choose simplify. Let's simplify the trig and see what we get here. That didn't simplify it too much. Let's go symbolic. Nope. Did a little bit more. It found a common denominator for us. It multiplied top and bottom by x and got this common denominator of x squared. So that's some progress, but still my answer was a little bit different. So if I want to figure out if my solution is equivalent, let's go ahead and recall what that solution was. Well, first of all, this is what Maple says is the right answer. So I'm going to copy that and paste it down here. Okay, then what I'm going to do is I'm going to put this in parentheses, and then from this subtract my function. So the function that I came up with, I'm going to subtract out, was x secant squared. Now this is kind of tricky. This is going to be secant of x quantity squared, okay, minus the tangent of x, all in the numerator, divided through by x squared. Okay, so usually I enter these a little bit separately, and I should have done that up here just because I like to make sure my function's correct. So I'm going to copy this piece right up here to make sure it's what I think it is. Whoops, a little too far there. Let's hit my semicolon. Let's see. Looks like I have a parentheses mistake. So I have arguments here. I have x times. I forgot to put in my asterisk for times. It's going to go down here. Let's try again. I think I'm still off by a parenthesis here. So I have x times secant of x quantity squared. I think I need to put parentheses around the entire numerator. Oh, there it is. X secant of x quantity squared minus tangent of x all over x squared. Now a couple quick notes. First of all, this looks like we should square the x, but that's not how Maple understands this. Maple understands this ambiguous notation as to being squaring the secant, not squaring the x. So be careful when you look at this, because it can be a little bit complicated here. So I think we have it all now, secant of x squared. So let's go ahead and hit enter here and see what we get. We want to simplify this, assuming integers, and we get 0. And that's good, because what this means is I took their answer minus my answer and got 0, so that must mean they're equivalent. So a lot of times, because you can rewrite trig functions so many different ways, this will happen. You'll check it in Wolfram, or you'll check it in Maple, or you'll check with your neighbor, and you guys will have slightly different solutions, but they are numerically equivalent just because I could rewrite them using trig identities. Okay, so we know this is the correct solution. We just checked it in Maple. I guess we could throw some of that Maple code in here. Okay, so let's go ahead and look at our solution, their solution comparison, and we got 0. Okay. So that shows that they're actually equivalent. So I did check my work, and they are equivalent. So this is the correct solution. So I've used just the good old power rule. I've used the product rule. I've used the quotient rule. And now I'm going to use the quotient rule again with a little bit more complicated expression. These are fun to simplify, especially when we get into these trig identities, because there's so many different ways that we can rewrite these. So let's look at the derivative with respect to x of the sine of x all over 1 minus cosine of x. Okay, we need the product rule here, so I start with the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Now let's be careful how we rewrite this. This is not 1 minus cosine squared, it's 1 minus cosine quantity squared. So make sure you write that correctly. Now from here, I haven't taken the derivative yet, I've just kind of set everything up, and I would really encourage you to write this out. That way you'll know exactly what derivatives you were taking and where they came from. So rewriting this, I get y prime or f prime of x, however you want to denote it, of the bottom function times the derivative of the top. The derivative of sine of x is cosine of x. So again, the derivative of the sine of x is the cosine of x, minus the top times the derivative of the bottom. The derivative of 1 is 0. Now I'm going to drag the minus sign along. The derivative of the derivative of cosine of x is negative sine of x. So again, the derivative of this piece right here is here. And this is all divided through by 1 minus cosine of x quantity squared. Okay, so let's go ahead and look at this. I'm going to distribute the cosine. So I'm going to have cosine of x times 1 is cosine of x. Distribute the cosine through here and I get minus cosine squared of x. Okay, now let's look at this. A negative times a negative is a positive. A positive times this negative is a negative sine squared of x. All over 1 minus cosine of x quantity squared. These are fun. Okay, if we continue to rewrite, I can see some trig identities coming up here. For instance, if I factor out a negative sign here, I'm left with sine squared. Actually, I'll stay in order just to make sure I don't trip anybody up. Cosine squared of x plus sine squared of x. That's a Pythagorean identity. Sine squared plus cosine squared is 1. So I can keep rewriting this. Now again, this up here, this is my derivative. This is the correct derivative. This is the correct derivative. I just want to simplify this down a lot because eventually I want to set these derivatives equal to 0, or I want to take these derivatives and set the denominators equal to 0. So I want to have them in a simplified form. Now, cosine squared plus sine squared is equal to 1. It's a Pythagorean identity. Sine squared plus cosine squared is 1. So when I rewrite this, I get y prime equals cosine of x minus 1. And again, it's obvious what the trig argument is because it's in parentheses. I don't have to wonder about that. I know that that minus 1 is not part of it. And then I look, man, these are so close to canceling. I'm just off by a negative. So what I'm going to do is factor out a negative in the numerator, and I'll be left with 1 minus cosine of x. And then if you notice, I have the same exact factor in the denominator, and I can do some canceling. So I can cancel this entire factor with one of these factors, and I'm left with a negative 1 in my numerator. So my first derivative is equal to a negative 1 in my numerator, all over 1 minus cosine of x. That's my derivative. So this is really easy to look at. I can clearly see that this thing will never equal 0 because the numerator is equal to negative 1, which can't equal 0. And I can clearly see that this denominator will equal 0 at the cosine of 0 radians. And also, if we were talking about radians, we could also talk about 2 pi radians because both of those have a cosine of 1. So when they're in their simplified form, it makes it a lot easier for me to evaluate. And we're not evaluating these right now, but we will be very soon, so it's a good habit to get into. Okay, let's go ahead and look at some more interesting problems. Let's find the second derivative. So let's find y double prime of y equal tangent of x. Now remember, trig identities, you could rewrite this as tangent is equal to sine over cosine and use a quotient rule if you wanted to. So a lot of different ways to do these. Now y equal tangent of x would be similar to your position function, and I'm going to the second derivative, which would be the derivative of position is velocity, the derivative of velocity is acceleration. Acceleration is the second derivative of position. So what I have here is basically find the acceleration function of the position function y equal tangent of x. Well, to find the second derivative, you have to find the first derivative. So y prime is equal to the derivative with respect to x of tangent of x. Okay, so the derivative of tangent is secant squared of x. Now, to find the second derivative, we need to take the derivative with respect to the first derivative, so we need the derivative of secant squared. Okay, so I don't know the chain rule yet, otherwise I could use the chain rule. So I'm going to have to write this out as secant x times secant of x and use the product rule. So let's go ahead and write that product rule out. So I have y double prime is equal to the first function times the derivative of the second plus the second times the derivative of the first. And then we can actually go through and take those derivatives. So the derivative of secant, remember you have to memorize those derivatives, is going to be secant of x tangent of x. So the derivative of secant of x is secant of x tangent of x. The derivative of secant of x over here is going to be the same thing. It's still going to be secant of x tangent of x. So rewriting, I have secant squared tangent plus secant squared tangent, which is 2 secant squared of x tangent of x. So that's my solution for the second derivative. Now if we wanted to work with this again and find the third derivative, we would actually have to take this and rewrite it as 2 secant secant tangent and then group my functions together and use a product rule. So this is my solution. I would also tell you that you could rewrite your solution. Secant squared is 1 over cosine squared. Tangent is sine over cosine, so you might also see this as 2 sine over cosine cubed. The exact same functions, exact same graph. It will evaluate the exact same way in radians. So again, these are pretty cool to do. These are fun because there's so many different ways you can rewrite them and so many neat trig identities that can be applied to them as well. Let's go ahead and look at another example. Let's look at y equal sine of x plus cosine of x times secant of x. Now this function to me is really interesting because first of all I see this as a product rule, so I could use a product rule here with this as my first and my second function, but I also look at this and think, I could distribute the secant and rewrite this and maybe make it a little bit more simple. So we could use a product rule. That could be one strategy. We could also rewrite, so we could actually distribute and then rewrite the function and then see what we have and take the derivative from there. And I could also try and again take some of these identities and see if I could apply any identities with the rewrite. Well, I would like to use the rewrite. So here I'm not taking the derivative, I'm just rewriting. I have sine of x times secant of x plus cosine, keep track here, cosine of x times secant of x. Now remember, secant is 1 over cosine. And also remember that you could use the product rule on this and be halfway done by now. It's cool to rewrite these. So here I see cosines cancel and I'm going to have 1. And then here I see sine over cosine. Well, that's just equal to tangent. So what I have here then is y is equal to the tangent of x plus 1. So if I want to find y prime, the derivative of tangent is secant squared and the derivative of 1 is 0. Just to write it in so we can see that. So therefore y prime is equal to secant squared of x. That's my derivative. Now I could have gone through and said the first times the derivative of the second plus the second times the derivative of the first and then simplified the heck out of that thing, but I still would have ended up with secant squared. So when you're working with these trig functions, the thing to remember is your Pythagorean identities, and your Pythagorean identities, just in case you don't remember them, are sine squared of theta plus cosine squared of theta equal 1. And of course, these could be anything. They could be x's or y's or z's. It doesn't matter as long as the arguments are the same. Another Pythagorean identity that follows directly from this is 1 plus tangent squared of theta is equal to secant squared of theta. And we get 1 plus tangent squared equals secant squared if we divide through by cosine squared. Now if we divide through by sine squared, right here, I'd get sine squared over sine squared is 1. Cosine squared over sine squared is cotangent squared. So my other Pythagorean identity is 1 plus cotangent squared of theta is equal to cosecant squared of theta. So these are the Pythagorean identities. You want to make sure you remember them because we use them a lot in calculus. Another thing you want to remember is your unit circle, because eventually we will be evaluating these. And of course your trig derivatives. Now we're going to be kind of adding to these trig derivatives a level of complexity when our arguments change, but for now we just want to remember our 6 basic trig derivatives. And again, the way I set these up is I think about the trig derivatives that start with the letter C, because I know those are all negative, so I usually write them over here so I can kind of group them together, because again it helps me remember that the solutions always have some value that's negative in them. For now, pretty soon when I learn the chain rule, I'll see that if I have a negative inside the argument of my trig function, I might get a positive value back. The derivative of sine is cosine. The derivative of tangent is secant squared. The derivative of secant of x is secant of x tangent of x. The derivative of cosine is a negative sine of x. The derivative of cotangent is negative cosecant squared of x. And the derivative of cosecant is negative cosecant x cotangent of x. And again, they simply need to be memorized. You just need to memorize them.